Second gas law we're going to deal with is called Charles' law. And Charles' law says that the volume of any gas and the temperature of any gas are directly proportional to each other. Now, again, let's talk about proportionality. So proportional means that they are going to change, and they're going to change by equal amounts, and directly tells you that it's going to change in the same direction. So if volume goes up, temperature goes up, and it goes up by the same amount, doubles. Again, just like in pressure and volume, everything else is going to be held constant, so pressure will be held constant in this situation. Now, we're going to be dealing with something that's totally new to us, and that is temperature in kelvins. Kelvins is an absolute temperature scale. So where in Celsius and Fahrenheit you have zeros and negative values, kelvins has no zero. Kelvins have no zero and no negatives. Really big when you're dealing with calculations, when you're trying to find a volume, that suddenly your temperature does not have negative values. So this way it means that your volume will always be a positive value. Like I said in the first portion, and when we talk about units, kelvins is found by taking your degrees Celsius temperature and adding 273 to it. Now you may have seen different numbers like 273.15. If you want to use the more exact number, that's fine, but 273 will work just fine for our purposes. This is the formula for Charles' law. It looks very similar to the pressure and volume, but now you've got V's and T's. But notice that the numbers changed places. Before, with pressure and volume, the 1s and the 2s were opposites to each other. Now notice that they are on the same. Okay, 1s on the top, 2s on the bottom, etc. Okay, so let's calculate something. Let's practice. A 1 liter sample of H2S gas at 20 degrees Celsius is heated until the temperature reaches 40 degrees Celsius. What is the new volume of the gas? Again, when you're working with any problem that has a formula, write your formula first. V1 over V2 equals T1 over T2. Write down what we know. We know the temperature at the first is 20 degrees Celsius. So I take my 20, I add 273, and I get 293 kelvins. Now my T2, it's raised to 40 degrees Celsius. 40 plus 273 is 313. Now I want to pause for a second and talk about something. Notice that in Celsius, the temperature has doubled, but in kelvins, they have not. Okay? This is big, really big, because on the surface, this looks like if the temperature doubles, my volume should double, and I'd expect a volume of 2 liters. But because we have to deal with kelvins here, notice it's not a doubling. So since it's not a doubling, I don't know what my new volume is going to be. I'm going to have to actually calculate it. Okay? My V1 is 1 liter, so I didn't even write that down. It's really easy. So let's plug in what we know. 293 for my T1, 1 liter for my V1, 313 is my T2, and now I'm going to solve for V2. Again, cross multiply and solve. So we take our 313 divided by 293, and we will get 1.07 liters. And of course, I will want to circle that at the very end to make sure my teacher can find it when he's trying to grade my assignment. Okay, so notice it only made a slight difference in the volume, even though I doubled my Celsius temperature. The difference in temperature in kelvins was not that great. Again, it was only a 20-degree temperature change, and so therefore it did not represent a big change in my volume. Also, I want to point out one more thing, that Celsius and Fahrenheit have a degree symbol. Kelvins does not. It is not degrees. Okay, so it's 293 kelvins, not 293 degrees Kelvin. Okay, make a little note on that on the side. 293 kelvins, no degrees. Let's calculate a few more. When 5 liters of carbon monoxide at a temperature of 50 degrees Celsius is transferred to a 2.5 liter flask, the temperature decreases. What is the temperature at this new volume? Okay, so first thing you do, write down your formula. V1 over V2 equals T1 over T2. Write down what you know. V1 is 5.0 liters. V2 is 2.5. 2.5 liters. My T1 is the temperature that goes with the 5 liters, so it's 50 degrees Celsius. So 50 plus 273 is 323 kelvins. And T2 is unknown because it says what is the temperature. So I'm solving for T2. So plug in my numbers. 5.0 divided by 2, over 2.5, 323 T2. Cross multiply and solve for T2. So let me punch it into my calculator real fast. So I've got 2.5 times 323 divided by 5 and get 161.5, but of course I have to round to two significant figures, so 161.5 kelvins will round to 160 kelvins, no decimal, because I don't want that 0 to be significant. Okay, notice a considerable temperature change. Why? Look at the volume. The volume went down by half. Therefore, I expect my Kelvin temperature to go down by a half as well. And it does approximately go down by a half. 323, half of 320 would be 160. And because of sig figs, that's why it came out the way it did. Let's try another one. When 0.75 milliliters of nitrogen gas at 20 degrees Celsius is heated, its volume doubles. What is the temperature in Celsius at this new volume? Okay, so again, with all these problems, please pause it so that you have a chance to solve it on your own before I get a chance to solve it for you. So write your formula. First thing you always do, write your formula. Also remember that not only is writing the formula useful because you can see exactly where everything is going to go, but it's worth a point on the test. And there's no reason to lose a point because you didn't write the formula. Now it says the gas is heated, its volume doubles. Well, okay, 0.75 times 2 is 1.50 milliliters. Not a very large volume. T1 is 20 degrees Celsius plus 273 is 393 kelvins. And it says, what is the temperature at this new volume? So I'm solving for temperature. So again, plug in my numbers. 0.75 over 1.50 is equal to 293. I know, some of you are thinking, oh, thank goodness he finally caught that. And then I solve for T2. Go to my handy dandy calculator, plug and chug. So I'm going to cross multiply 1.50 times 293, enter, divided by 0.75, 586 kelvins, but once again, two significant figures, so I'm going to round this to 590 Kelvin. Okay, now, some of you are looking at these two problems, and you're saying, well, wait a second, Mr. Siegel, you keep saying it's got two significant figures, and you keep pointing to the volume, but you never looked at the temperature. This temperature only has one significant figure, and you're absolutely right. That's a true statement. Temperatures in Celsius typically only have one or two significant figures, but I didn't use that number in the calculation. I used kelvins. So whenever you're evaluating the significant figures, compare the Kelvin temperatures to the volumes instead of the Celsius, okay? So in sig figs, always go for sig figs, you're going to compare the K temp, okay? So kelvins are typically going to be three significant figures, so I can compare the three significant figures in Kelvin versus the two significant figures in the volume. I did the same thing in the previous problem too. Notice this only has one significant figure, but my volume had two significant figures. But I don't look sig figs here, I look at the sig figs in the kelvins. The kelvins here have three significant figures, 3, 2, 3, but 2.5 and 5.0 are only two significant figures. That's why my answer must come out in two significant figures. So again, for when you're doing sig figs, you're going to compare the Kelvin temperature versus the volume or pressure or whatever it happens to be. And those are Charles' law examples.